Hi, okay, um, this is a screencast of equations and motion maps and graphs and all the theoretical stuff of velocity or constant velocity, um, zero acceleration, and um, increasing velocity and non-zero acceleration. So what we have here is a situation where we have a car that's traveling in a constant velocity. We know that the velocity is constant because we see that we look at the arrows or the motion map, which shows like arrows of velocity, and we look at the arrows, and the arrows are all of equal magnitude, pointing in one direction. So that would mean that constant velocity in one direction, and then we don't see any acceleration arrows, so no acceleration. And then I drew the graphs. The position time graph shows that the it's constantly increasing its position as it travels on. Um, and the position is the increments between the position is perfectly like equal to each other. So there's no yeah, so it's increasing it's just increasing at a constant rate. And so when we look at our slope, um well, okay, so when we look at our slope, or the velocity, we'd find that we have a velocity, but the velocity doesn't really change over time. It's the slope of our velocity would be like zero, so that's why our acceleration is zero, because it doesn't really change. Again, I want to say that this is not real life because there's no way the car could ever travel at a constant velocity, zero acceleration, just impossible. But anyways, so to find your final position along this line, or just like for this problem, what you would do is you would find um the displacement of your position, which can be found this uh, beneath the velocity. So pretty much your displacement is just the area of your velocity time graph. Um, so the gray shaded region, that's when you find the area of that, then you add the area with your initial velocity or initial position, then you'll find your final position. And the reason why you do that is your displacement is the change in your position. It's the difference between where you started and where you ended up. But the thing is, your position is in relation to zero position. So like, what's the ultimate zero? So it just means, so to find like final position just means that like you'll see how far you traveled, but then you add up like how far you've started in. So let's say your initial position, or you started at driving at, let's say, 100 meters, and your zero position would be your house. So you started driving 100 meters from your house. Um, 100 meters away from your house. And your displacement, or your change in position, would be, let's say, 200 meters. So your final position isn't 200 meters. That's only your displacement. That's how far you traveled. But you haven't factored in yet where you started. So if you're looking at your final position and your starting position is your house, then your final position would be 300 because you started 200 or 100 meters away from your house, and then you drive another 200 meters, and so that's how far you are from your house, right? Okay, so that's that. And then, like I said, oops, a little too far. This is this is showing what happens when your um, acceleration is no longer zero. You have an acceleration, and so you see that the relationship between your position and time goes exponentially. Is that how you say? Exponentially? Yeah. Um, so it goes exponentially. And so this is what the model would look like. You're driving, right? And so the yellow arrows indicate your velocity. The green arrows indicate your acceleration. So your velocity over time is increasing. Your acceleration over time stays the same. Okay, so why is that? So, okay, so before we explain why that is, first we draw the graphs. So when you draw the graphs, you see, again, position and time, and the relationship goes exponentially. And then when you find the relationships when you find the relationships um, between the position and time of like 2 points, so you find the slopes of every 2 points on this graph, and you graph those slopes, you'll get that your velocity time graph increases in equal increments over time. So it would look like this. And so when you find the slope of this, you will see that your acceleration time graph, so there's one slope. So you only have one acceleration, right? It doesn't change over time. So the slope of your acceleration time graph would be 0. But you have an acceleration. Okay, so keeping that in mind. To find our final position in this situation, what you do is you get 1/2 of your acceleration times your time squared. You add that to your initial velocity times your time, and then you add your initial position. Okay, so next, before I get ahead of myself. Okay, so next, to find, okay, by the way, first of all, we got this equation, the equation for final velocity, using our equations over here. You see, because the 1/2 at squared, acceleration times time squared, we found using, by getting the area of our velocity time graph, so that really hasn't changed. And then we got the v naught times t by getting the area of the acceleration time graph. Now, why didn't we do that in the zero acceleration situation? Well, the thing is, you technically already did that. You just didn't see it at first because you had zero acceleration. There's no point in doing this step when you know it's 0. You're just adding 0 to the problem, which doesn't really make a difference, right? But you technically did that. So, okay, so what was this? And then your initial position, and I had my whole spiel about that. Alright, okay, so, as to why you're adding your initial position. Okay, so next. Velocity, okay, so you find final velocity by multiplying your acceleration times your time and then adding initial velocity. This situation is the same as previous situation in the zero acceleration position graph. You get the AT by finding the area of the acceleration time graph, and you add your initial velocity, and that's why you get final velocity. And then your acceleration is equals to your change in velocity, or the relation. Yeah, it's the change in velocity. Wait, no, it's not. This is wrong. Haha. Can you disregard this? This is wrong. Okay. So your acceleration is actually the slope or the relationship between velocity and time. What should be written there actually is acceleration equals velocity over time. And if we find our velocity over time, we'll get that it's one specific number on all the points. That's why when we graph the relationship, there is velocity over time for all the points, we'll see that it's all the same number. That's why our acceleration would have a slope of 0. Okay, so moving on, displacement or the change in position. So the change in position would be 1/2 at squared plus v naught times your t. So that's you're getting the area of your velocity time graph and your area of your acceleration time graph, and you're adding those two together. We'll also see that that would equal your final position minus your initial position, which makes sense. If you subtract the initial position up here from both sides, we'll get final minus initial would equal 1/2 at squared plus v naught times 2. And so that just means that if you want to find the difference between where you started and where you ended, that's how you do it. The difference between displacement and your position is that displacement is actually in relation to wherever you started. Position is in relation to wherever your ultimate 0 point is, or yeah. So if you're going back to that house example that I was giving, where you're driving, so that would mean your initial or your ultimate 0 starting point would be your house. Everything is in relation to your house and how far you are from your house, right? But then your displacement is that 200. It's you started 100 meters away from your house and you traveled 200 meters. That 200 meters, that change in position, that's your displacement. And so, yeah.